Okay, so in this recording, we'll go through examples for two sections. 6.1 is velocity and net change. And this section, I would imagine, it was fairly easy for most of the students because we haven't really learned much here, much new. We've done problems like that in calculus. We just put in a little bit more of a new notation here. So here I'm giving you a quick outline of what was covered in the videos, but I'm just going to go ahead and jump straight to examples. Okay. And these notes, the completed notes, will be converted into a PDF file and uploaded on your course site a couple of hours once this lecture is finished. Okay, and that's going to be every lecture. Anytime you guys see me write something using an iPad, I will post the lecture notes later on. Okay, let's go ahead and take a look at the first example. We have a function v of t, where t usually represents time. It's a cubic polynomial on an interval 0 to 5, and we would like to answer the following questions, so we're going to take them one at a time. The first one says, determine when the motion is in the positive direction and when is it in the negative direction. Okay. All right, so what we're going to do first to answer this question, we're going to take our function and split it, and what I mean by that, factor it, because we would like to see where we have change of behavior. Okay, once you factor your cubic polynomial, we have zeros of this polynomial, right? So 0 is one of the zeros. Okay, then we have positive 1 and positive 5. Okay, we need to determine where this motion is in a positive direction and when is it in the negative direction. Okay, so what do we do here? We need to see where this function is positive and where it's negative. So we could just use sample points from these intervals to determine what is the behavior of the function. So pick any point. Okay, so let's say from 0 to 1. Okay, so on the interval from 0 to 1, not including. Okay, what is the direction here? We need to pick any point that's in that interval, right? So let's pick 1/2, and we just need to see what the sign of this function is. Okay, well, once you plug it in, what we're gonna get? So the first factor will give us plus 1/2 minus 5, that's minus, right? That's negative. And then 1/2 minus 1 is also negative. Okay, so positive times negative, that would be positive. So we have positive direction. Okay, similarly, you can pick any point in the other interval. So let's say 3. Okay, so on the interval, we're not including that 1, from 1 to 5. Okay, let's see, if we'll plug in 3, we get first positive term, second positive, and second is negative, and the other one is positive. So we get negative direction. Okay, what does it mean? Once you pick a reference point, so let's say you pick your reference point 0, then you decide, north is positive, south is negative, right? So that's what it means. Whatever your setup is, okay? One goes in the positive direction, another one is negative. All right, so the next question says, find the displacement over the given interval. The displacement, that part is easy, right? We just need to integrate our function. 4t cubed minus 24t squared plus 20t dt. This is a polynomial function. It's easy to integrate. Okay, so what is the antiderivative? We get t to the fourth minus, let's see what happens here, 8t cubed plus 10t. Is that right? T squared. There we go. Okay, you can always check if this is correctly by differentiating. So if I take the derivative, that's 4t cubed minus 24t squared plus 20t. Now this is a definite integral. We evaluate it from 0 to 5. Okay, at 0, everything is 0, it vanishes. So then we get 5 to the fourth minus 8 times 5 cubed plus 10 times 5 squared. The answer should be negative 125. Let's give it some units. So let's say meters. Okay, so this is our displacement over the given interval. We go from 0 to 5. Okay, displacement, it is the total distance, right? So what happens from the reference point, that means what? We displaced 125 meters in the negative direction, whatever that direction means. Okay, now the next question says find the distance traveled over the given interval. Okay, and you say, well, wait a minute, isn't that the same thing? Okay, that is not the same thing, because we traveled in two different directions, right? So the distance traveled is something different. Okay, so here we would split up our integral in two parts. So let's say distance number 1 from 0 to 1. Okay, and we integrate our function from 0 to 1. We want to see what happens there. Okay, so once you do this, I'm going to let you check the work. It's the same integration, evaluate from 0 to 1. We're going to get 3 meters. Okay, what about the other part? Distance from 0, not 0, from 1 to 5. Okay, from 1 to 5, if you integrate this function, we know the antiderivative, evaluated between 1 and 5, we're actually going to get 128. Okay, 128. But we know that on this interval we were going in the negative direction. So really, this is negative 128 meters. Okay, because we know that we're going in the negative direction. And no, once we add them up, negative 128 plus 3, that is negative 125, which is your total displacement, right? Okay, so for these problems, we just need to be careful and see what is it that they ask. Do they ask for displacement, or are they asking for total distance traveled? Okay, so what is the total distance traveled? We didn't answer that question yet. Total distance is what?
The absolute value of integral of v of t.
So what would be the number here? So the actual number, 131, Christopher says, right? Yes, good. Okay. The total distance traveled is 131. Very nice. Okay. Displacement is different, right? Displacement is different. Total distance, we'll look at the sum of those two integrals. Okay, 128 and 3. Okay. All right, let me take a minute here. Oh, I'm missing a negative over here. Otherwise, it's going to be negative. Okay, let's take a minute here. Are there any questions? Anything that you would like to discuss for this problem, just this problem in particular? You can raise your hand. You can just type up the question. If not, we're going to keep going. Okay, let's see. Somebody raising your hand, go ahead.
Yeah, I was just gonna say, if I'm not mistaken, that's not the same results that the video that we initially watched came to.
Not the same result?
No, not the same answers.
Was this problem in the video? I thought I picked different problems. Was this particular problem?
I'm looking, I'm verifying.
Okay.
It appears to be the same problem to me. It appears
And what do they get?
they're getting negative 125 meters for the displacement, but the distance is they get 147.
They get 147.
Yes, ma'am.
How? Let's check this.
Sure.
Let's see. Well, okay, so if it's they get negative 100, so do they get 128 for the second one?
For the displacement value over 0 to 5, they got negative 125 meters.
Mm-hmm.
And
Okay.
then for the distance traveled over 0 to 5, they got 147 meters.
For D1, you got 19. Let's see if I made a computational mistake. All right. So let's do this then. From 0 to 1. This is not a good start, but I was pretty sure I've done this correctly. Okay, from 0 to 1, 4t cubed minus 24t squared plus 20t dt, right? That's our function. Did I copy this right? Yes. Okay, let's see. So this is t to the fourth minus, the function is still the same, 8t cubed plus 10t squared. We go from 0 to 1. Okay. So if we evaluate this from 0 to 1, that's 1 to the fourth minus 8, 1 cubed plus 10. Isn't that 3? Okay. So this is correct. It's 11 minus 8, right? So that should be okay. And it's 3, and we're going in the positive direction. So that matches. Okay, if we evaluate this from 1 to 5, we should get a negative 128 unless we put that negative up front. Okay, well, how about this? I'm confident my answer is correct. I mean, unless you guys see an obvious mistake, I don't think this is wrong. Christopher, you say yes for what? Oh, somebody's raising your hand. Somebody raising a hand.
Yeah, the only difference I see is when they distributed the negative all the way through and their problem, and you just put yours in the front and then did it afterwards. I don't know how they got different numbers though.
Yeah, I'm gonna look through that video again carefully and see what's going on, because I'm fairly certain this is arithmetics, right? This is just plugging in numbers in a polynomial. I think this is correct. Do you guys see any glaring mistakes?
I wasn't necessarily challenging your answer.
Oh, no. Yeah.
I was more just wondering why it was the same problem with two different answers. That's all.
That's a good question. I don't have an answer to this one.
Okay.
But okay, do you guys believe me? This is correct. Yeah. So I am curious now. I carefully went through most of them, just making sure that they cover the right topics, and I guess I missed that one. Was that the first problem too that they discussed?
That was the first problem. Yes, ma'am.
Wow. Okay. So interesting. All right. So I'm convinced the solution that you have right here is correct. And I'm going to write a nice letter to Pearson saying, hey, what's going on? I'll check it. I'll check it. Maybe, I don't know. I can't imagine why they would get a different answer. So I'm glad that this came up. All right, so do you guys see how the total displacement is then? What is the total displacement? I erased it, but this was correct. What is the displacement? It was 128 for one of them plus 3, so that's 131, right? Now 128 was in the negative direction and then 3. So are you saying they getting, what are they getting? 100 and
Getting 147, and what the work that they provided beyond what you provided there was that they did they took the integral from 0 to 1, then added the integral from 1 to 5,
okay.
except the negative of it for the sake of the absolute value.
Yes.
So
okay, yeah. So what is that? That's 3 plus minus minus, right? So that's 3 plus 128. So did they not do evaluation correctly? Or maybe I didn't do it. I think I'm.
On your step number 2, you're evaluating it from 0 to 5. Should that be from 1 to 5?
no, not on step 2. It's the second part of step 3.
Second part of step 3
would be evaluating from 1 to 5 instead of 0 to 5. Because the step 2 was evaluating from 0 to 5. The second part of step 3 would be evaluating from 1 to 5, because from 1 to 5, the value is, it's a negative value, right? So you have
from
to,
1 to 5, we should get a negative value. Yes.
so the second part of step 3 is to add to it the integral
Yes.
from 1 to 5, not 0 to 5, right?
From 1 to 5, that's your distance, right? What did they get 125 as well?
On the displacement, they got negative 125 meters.
Okay.
So
Yes.
the other gentleman asked if
Uh-huh.
the other gentleman asked if step 2 should have been from 1 to 5, but it should have been. It's actually the second part of step 3 should be 1 to 5, correct? Because you're evaluating
Yes.
from 0 to 5,
That's
but you're
right.
evaluating from 0 to 1 first, positive, and then you're adding to it the
That's right.
negative from 0 to 5. From
That's
1
right.
to 5, not 0 to 5.
I just erased this, right? I erased it to make more room for this problem. So when I wrote this problem initially, we did from 1 to 5, that integral.
Okay.
Okay. Yes. So no, the idea is you. Okay. So Zachary says, I think it was their error. I'm going to just go through that video carefully again, and we'll make it clear. But
Thank you.
yes, no, definitely bring this up. This is a good discussion, because I think it's also makes sense for us to understand every single step here, why we do what we do. So let me just do this real quick. 8:43. Okay, that's where the work is. So let me make real quick this note right here so we can keep going. This interval ends up being 3, and we've checked the work, right? So then from 1 to 5, v of t dt. If we evaluate this function, t to the 4th minus 8t cubed plus 10t squared, we go from 1 to 5. What do my notes say? I'm just going to be careful here. My notes say negative 128 if we evaluate it as is. Okay, so that's negative 128, which makes sense because this is a negative direction, right? Oops, too far. Okay, so if we take the negative of it, then we get just the distance without the direction. Okay, so then the total distance should be 3 plus 128. Okay, I'm going to double check on this problem for sure. Okay, all right. Great job, everybody. Okay, let's take a look at a couple more problems here. Let's see. So we're getting into more involved functions. So that was the polynomial function. Okay, we know how to differentiate that. Here in problem number 2, they ask us to determine the position function using 2 methods. Okay, so something we've done in calculus 1. And now the second part says determine the position function using the fundamental theorem of calculus, which really is the same type of method, just slightly different notation. Okay, so method number 1, just using the antiderivative. We have the velocity function, we have the initial condition. The position function is just the antiderivative of v, right? So position function s of t is the indefinite integral. And what's our function? 3 sine pi t dt. Okay, so what's the antiderivative? Would be negative 3 over pi cosine of pi t plus a constant, right? Okay. If you've taken calculus 1 recently, you might remember this type of problem, because usually we kind of finish up our class with the problem of this type. Okay, you have initial condition, find a function that satisfies these conditions. Okay, so we're not quite done yet. We need to decide that C is. We have initial condition S of 0 is 1. Okay, so we'll plug this in into our function. Cosine of 0 plus C is equal to 1. Okay, cosine of 0 is 1. So we have negative 3 over pi times 1 plus C is equal to 1. So from here, we can find our C. So for C, it's 1 plus 3 over pi. Okay, so your position function is that 1. S of t is negative 3 over pi cosine pi t plus this constant. Okay, that is your answer using one method. Okay. Second solution to the same problem, determine the position function using the fundamental theorem of calculus. Okay, S of t, then you would be using this formula right here. You basically combining the integration with limits here and the initial condition in one step. Okay, so S of 0, that would be 1 plus the integral from 0 to t 3 sine of pi over pi x dx. Okay, so this is 1 plus the antiderivative, we know what that is, negative 3 over pi cosine pi x, and then we go from 0 to t for the evaluation. And look what happens, we get exactly the same function, right? Okay, so plus negative 3 over pi cosine of pi t. So that's that. And then cosine of 0 is 1. So we get minus minus, that gives us a plus. So this is plus 3 over pi. And we get the same thing. Here and here, this is the same function. Okay. Now, let's say you have a problem like this on a quiz or on a test. Which method you want to use? Doesn't matter. Pick one. Okay, whatever is more convenient for you. But it's a good idea to kind of see both notation. Really, they're not different methods. They're just slightly different notation. Okay. All right. I'll stop right here for a minute. Do you guys have any questions on this problem? Is this okay? All good? All right. Then let's keep going with a little bit more problems of this type. Okay, let's see. This is one of my favorite types of problems, and you'll see in a minute why I like this problem. Okay, so what do they want us to do? Same idea. We have this function on a bounded interval from 0 to 8. We have an initial condition. We want to find the position function using two methods below, antiderivative and fundamental theorem of calculus. Okay, all right, let's do the first method. Okay, so we have the velocity function. We need to integrate this. Okay, so we're going to integrate 1 over t plus 1 dt. Okay, what is the antiderivative here? Does anyone know? One over stuff. And if that stuff is linear, that's nice, because that's a very high chance this is a natural log. So this is how you can think about it. If you have 1 over some stuff that's in a linear form, meaning there's no powers, right? So we only have t plus 1, t is to the first power. This is natural log, okay? So this is natural log of t plus 1 plus c. Okay, so you will see that in this class we're going to do a lot of integration, and we're going to learn about integration techniques. So things like U substitution, you know, trig integration, all of those things we just kind of need to keep in our back pocket and try to remember. Okay, but here's, you know, kind of like a little trick. If it's 1 with the stuff on the bottom that doesn't have any powers, try natural log and see if that works. Okay. All right. So that's natural log of absolute value of t plus 1. We need to find that constant c. So natural log of t plus 1 plus c is equal to what? -4 if t is equal to 0. That's my initial condition, right? Okay. So -4 and 0. All right, so once we plug this in, we get natural log of 1 plus c is equal to -4. Natural log of 1 is 0, right?
0. Yep.
Good. So we have 0, c is equal to -4. Okay, so that means our function, our answer is natural log of absolute value of t plus 1 minus 4. That is the position function that satisfies this initial condition. Okay. All right. Second part. Using the fundamental theorem of calculus. So our initial condition is still -4 plus the definite integral. We're going from 0 to t, and now I introduce some dummy variables. So this is 1 over x plus 1 dx. Okay. We get -4 plus what? Natural log of absolute value of x plus 1. We go from 0 to t. T becomes the variable, okay, plus natural log of absolute value t plus 1 minus natural log of what? 1, but that's 0. So we get -4 plus natural log of t plus 1. Okay. All right. You see that both produce the same answer. Okay. And I'll say it again. If you guys are faced with a problem of this type, choose your method. I typically won't ask you to do both. Just one is good enough. All right. Okay. Let's take a minute. Any questions on this? Nothing? Okay. All right, let's do one more problem, and then we'll move on to the other section, which I feel like is a little bit more involved. So here we keep going with applications of differentiation. Nothing completely brand new here. We're still working with a function with the velocity. So now we say, okay, how do we find velocity given acceleration? Okay, that's similar to how we find distance or position function given the velocity. So find the position and velocity function of an object moving along a straight line with the following condition. So we have acceleration function given to us, but now also notice we have velocity and position initial conditions, right? So you say, okay, hold on, I have acceleration, which means I can find the velocity, and then if I integrate again, I can find the position. But I need two conditions, right? I need to know two initial conditions. Okay, so here, the first function that we're going to find will be velocity. Okay, I'm going to use this formula here, v of 0 plus the integral. Okay, so v of 0 is 20 plus the integral. We go from 0 to t. Now you write your function with dummy variables. So this is 20 over x plus 2 squared dx. Okay. So how would you integrate this? Now you take a look at it and you say, I have 20 over stuff, but it's no longer linear. So this is not a problem where we should say, oh, this is just natural log. Okay. That expression in the denominator is raised to the second degree. Okay, second power. So this is not natural log. Then what is it? The next natural step to try is u substitution, and u substitution in this case will work. Okay, you can work out the steps. X plus 2 would be your u. Okay, once you work this out, you're gonna get 20 plus negative 20 over x plus 2. Okay, you can also think about as x plus 2, 1 over x plus 2 squared as x plus 2 to the negative second power. Okay, and then you say, oh yeah, so this, you can apply the power rule and find your antiderivative. So your antiderivative in this case is negative 20 over x plus 2. You can check real quick. If you take the derivative of this, you should get the expression in the integrand. Okay, and we evaluate this from 0 to t. Okay, so we're going to get 20 minus 20 over t plus 2. I'm just plugging in t. And once I plug in 0 for x, I'm going to get negative 20 divided by 2, that's negative 10. But plus, minus minus will give us a plus, right? So we get plus 10. So the final answer is 30 minus 20 over t plus 2. Okay. All right. So u substitution method will be used a lot. In fact, your first non-graded assignment, but we could discuss it at any point, is to review integration. I posted a package on Blackboard, right? You guys work through it on your own pace, and then maybe next Wednesday we'll discuss it actively. Okay, but all of those problems will basically ask you to solve an integral using the u substitution method. Right, so this is your velocity function. Okay, now we need, yes, I see somebody raising the hand. Go ahead.
So for the non-graded packet,
Mm-hmm.
you actually, are we actually supposed to upload our full work for all of those problems, even though you're not going to grade them, or are we just supposed to attempt them and then you're going to go over them in the class and you'll never actually see what we've done?
What would you like? Would you like to submit it?
Not necessarily.
Okay.
But I was just curious. I was just curious what the expectation was.
So okay.
So we
So
can
yeah. So my expectation was that you do not submit it.
Okay.
Unless you want to. If anybody wants to submit it to me for feedback, That's fine. I'll create a quick button on Blackboard where you can submit it, and it will count as just, you know, non-graded, you know, just feedback. If that's what you want, definitely let me know. In my classes that are face-to-face, I assign it as a graded assignment. So students actually, I collected by hand and graded. But again, I'm trying to make this semester a little bit less stressful. We still need to learn things, right? But I'm giving you a little bit of a break from different assignments because it's going to be tough enough.
Much appreciated. Thank you.
Yeah. Okay, so if any of you guys want me to take a personal look at your assignments to see how you write them, that's great. But keep in mind, after this week, there will be an assignment that I will collect for grading. So I'm basically kind of giving you an easy start. And then every 2 weeks, we will have assignments that I will collect for grading through Blackboard. I'll give everybody feedback. It's just this one. So sorry, good news, but not that great. There's still more work coming. All right. Does everybody actually know what I'm talking about? The review packet? There's 15 integration packets. Take a look at it at some point. It will kind of give you an idea of what the expectation is, so that you know how to solve these problems. All right. Okay. Let's see. So we've done. Well, we solved for V. Let's go ahead and solve for the position function. Okay, position function is the antiderivative of the velocity function, which we just found. So now we use the condition 10, right? Our initial condition is 10 plus the integral. We go from 0 to t. And what is it? So we integrate in 30 minus 20 over x plus 2 dx. Okay, we have our initial condition. We have the dummy variable x, and we have a function to integrate. So 10 plus, what do we get here? This is 30x. And now I'm looking at this expression, and once again, I have 1 over linear function. This is natural log. Okay, minus 20 natural log absolute value of x plus 2. We evaluate from 0 to t. Okay, so let's evaluate this carefully. 10 plus. Okay, so once we evaluate everything at t, we just get a function, an expression in terms of t, right? So that's 20 natural log absolute value t plus 2 minus, and then 0 times 30, that's 0, so okay, that's fine. Minus minus, that gives us plus 20 natural log of 2. Okay. All right, so the last step that we could do, we just combine everything that contains t. So what do we got? 30t minus 20 natural log of t plus 2. And then the constant terms are 10 and 20 natural log of t. Okay, not a very pretty answer, but that's what that is. All right. Okay, you guys have any questions on here? Anything that you would like to discuss?
Nope. Feel all right about it.
That's good. That's good. Okay, so this problem right here, I'm gonna make a note here, try on your own. Okay, very similar to what we've done in example 4, except now you have a trig function, right? So see if you can work this one on your own at some point, not right now, okay? Because I do want to talk about areas, okay? Areas between curves. So let me go back to my other section. Okay, area of a region between two curves. Okay, that was the other section that we've covered. Okay, again, fundamentally, we did not learn something groundbreaking, something brand new. Okay, you already knew that if you have a function and we're integrating this function on the interval from a to b, you already knew that what we're finding is the area under the curve, right? So that is part of the fundamental theorem of calculus from calculus 1. But now what we're saying, okay, but what if we don't just have the function and the x-axis? What if we now have two functions that bound a region in a plane? Well, we can still find the area of that region by integration, okay? And the formula says you subtract the two functions, one top and one bottom, and you evaluate your new function on that interval, okay? So let's go ahead and do as many problems as we can here until our time is up. So what do we have? Oh, we have plenty of time, 1:50. Okay, all right, let's see. So first example says find the area of the region bounded by the graphs of these parabolas. And a good question might be, well, okay, if we have this problem, how do we graph it? So I am completely fine with you guys using Desmos for the entire semester. Okay, go ahead and show you what that app looks like. Okay, you are free to use this application anytime you need to graph anything. Okay, on exams including, that is completely okay. So I'm going to type in my first function, y is equal to negative x squared plus 4x. Okay, that's my first parabola. My second parabola is y is equal to x squared minus 2x. Okay, so we're trying to find the area that's bounded by these two parabolas. Okay, which means we need to determine where these two parabolas cross, right? Well, one point is obvious, 0, 0. And that's the beauty of Desmos. You can just touch that point and it tells you exactly what the coordinates are, okay? And then the second point is 3, 3. Now, just for the sake of argument, suppose we don't have this graphing utility. How would you guys find the points of intersection?
Set the equations equal to each other.
That's it. You got it. Yeah,
factor it out and do
you would
whatever.
solve it algebraically. Good. So you can use Desmos to get a good idea what the picture looks like and then just sketch it. It doesn't need to be super accurate, just a basic idea. What is it that we're trying to find? Okay, this area right here, I'm going to shade it. Okay, so we have 0.00 and 3, 3. That's where they cross. You can either solve it algebraically by setting f of x is equal to g of x, solve simple quadratic equation. You'll see that it's easy to solve. Okay, or you can just look at the graph. That's completely fine. So now we need to find this area. Okay, we're going to find this area from 0 to 3, right, on the x-axis. Okay, now which one is the top function, f or g? Right, it's a good question. Is the area that you get from two functions always positive? Yes, that's a great question. Yes, it should be positive. Because we're not, right now, we're not concerned about what's below, what's above, right? We're looking at the total area that we bound, okay? You should always get a positive number. Very nice, thank you, Zachary. Okay, so, but notice what would happen. So f, if you just find the, G is top, yes, so if somebody answered the question, G is top, is G top? I think f is top, right? Isn't f the top function? F is the function, the top function is the one that opens down. That's the parabola with the negative coefficient. So we get negative x squared plus 4x minus g is the bottom. That's the parabola that opens up. So the positive leading coefficient dx, okay? We get the integral from 0 to 3 of what? Negative 2x squared plus 6x dx from 0 to 3. Okay, oop, no, I'm going to integrate it. This is polynomial. It's easy to integrate. So what do we get? Negative 2/3 x cubed plus what? 3x squared, right? We go from 0 to 3. At 0, everything is gone. So at 3, let's see, what do we get? Negative 2 over 3 times 27. One of those 3's cancels out. Okay, so we get minus 18 plus something. Minus 18 plus 27. Okay, we get 9, right? 9 what? This whole thing is 9 units squared. Okay? Now let's see. So that would be how you find this area. Okay, so step by step, I would always recommend make a picture and use Desmos or any other utility that you'd like. I think Desmos is very user-friendly. You can download the app for free, or you can just use a browser. Okay, find your points of intersection, carefully integrate. We should be good to go. Okay, any questions here? Is this okay? How are you guys feeling so far? It's been about an hour. Somebody's raising their hand. Go ahead.
Doesn't subtracting out the the g of x out, doesn't that just take away the area that's from where the where f of x intersects the horizontal, intersects 0, or yeah, 0, whatever that is, 0, 2, it looks like. Isn't that just subtracting it from 2 to 3, or is that adding that under area also?
So, okay, I think I know what you're asking. I know what you're asking. You're saying, okay, we're subtracting, right? We're subtracting. Let me highlight this part. See if this is the part that you refer to. Like this part right here?
Yeah.
Sorter, yes. Well, if you were to just integrate this part right here, right? So let's say you integrate g from 0 to whatever, right?
Mm-hmm.
You're going to get a negative number, correct? Correct?
Yeah.
Yes.
Oh, okay. That's why. Okay.
Right? That's why we're subtracting.
Okay.
Yeah. So technically, when you guys were doing your area, so let's say I'm going to put a little picture here, and I'll probably delete it. But let's say you go from here to here. I don't know, let's say from 2 to 7. That's what you integrating, right? Technically, you were doing the integral of f of x minus 0 dx. 0 being the x-axis. Okay, so we always had that subtraction. It's just that other function was always the x-axis. It was bounded, right? That was your bound. And now here, for this example, our lower bound is no longer the x-axis. Our lower bound is another function. Does that make sense? I don't know if that helped. Maybe
Yeah,
even
yeah,
more.
that's
Okay. Okay, good. All right. Okay. But yeah, you're right. Like we're subtracting a negative area, right? So we're actively adding the area, we're making it positive. Okay. All right. Let's see. Let's take a look at another example. Now we have trig functions. So we have a sine function, negative cosine function. The interval is from negative pi to pi. Once again, I'm going to go to Desmos. Okay, and graph it here. Y is equal to sine of x is my first function. Okay, and my second function is y is equal to negative cosine of x. And what else you can do, we can actually put our bounds. What are the bounds? From negative pi to pi. So we can say x is equal to pi. And I need to find pi. Let's see, we can just type in pi. So here's 1. And then x is equal to negative pi, right? Negative pi. Okay. All right. So that's what we get here. Okay. We would like to find the area bounded by these curves. Okay. What do you guys think? How would you approach this problem? Yes, somebody's raising their hand. Go ahead.
You would find where they intersected the 2 times in between there, and then you would set up an integration for in between both, or for all 3 of the sections, switching which
Okay.
one was the top and bottom curve.
Okay. All right. So do you see that we would have to have how many? We would have to have
The
3
3
integrals,
sections.
right? 3 sections. Okay. Well, just to save some time, let's go ahead and find the area just between these 2 points, negative pi over 4 and 3 pi over 4. And then you'll see that you can add the other ones, right? So the integration will be the same, just the evaluation will be different. But here, yes, you would have to have 3 integrals. One from negative pi to negative pi over 4. Then we have from 3 pi over 4 to pi, and then the one in the middle. But let's take a careful look at it. Is there one way we can just do it? If we go from negative pi over 4 to 3 pi over 4, isn't it just double of that and we get the whole thing? Do you guys see it? I can't use the cursor on my on my iPad, but carefully take a look at the pieces that we get. The little piece on the right and the bigger piece on the left. If you combine those two, we're going to get what's in the middle, negative pi over 4 to 3 pi over 4, right? Okay. So let's find this piece in the middle. From negative pi over 4 to 3 pi over 4. Okay. Now, which function was top and which one was bottom? Let's go back. Okay. Let's see. The green one is sine. The purple is negative cosine. So on that piece right here, on this interval, from negative pi over 4 to 3 pi over 4, the top function is sine. So we have to be careful because look, on the other sides, it's alternated. So if you were to set all 3 integrals, we have to be careful which function is top, which one is bottom. Okay, but we can just find this one area between negative pi over 4 and 3 pi over 4 and double it. Okay, so in this case, sine is the top function minus negative cosine. So that would be plus cosine dx. Okay, let's see. The antiderivative of sine is negative cosine. The antiderivative of cosine is positive sine. And we need to evaluate this from negative pi over 4 to 3 pi over 4. Okay, so we're going to carefully evaluate this. So negative cosine of 3 pi over 4 plus sine 3 pi over 4 minus, so that's plus cosine of negative pi over 4 minus sine of negative pi over 4. Now, all of these values will be the same in absolute value, right? We're dealing with root 2 over 2. The question is, are they positives or negatives? So 3 pi over 4, that is what? Third quadrant, right? Nope, that's second quadrant. In second quadrant, cosine is negative. Minus minus gives us a plus. So this is root 2 over 2. Still second quadrant, so this is also root 2 over 2. Let's see, cosine of negative pi over 4. Negative pi over 4, that's fourth quadrant. Cosine there is positive. Sine in fourth quadrant is negative. Minus minus give us a plus. Okay. All right, so how many of these we have? 4. 4 root 2 over 2, so that's 2 root 2. Okay, so let me make this sketch real quick. See if I can copy that sketch the best I can. All right, so we have our sine function here, and then cosine on that interval. Let me see if I can do it. Something like this. Okay, the cosine was below, so negative cosine x over here. So the piece that we found is this piece right here. Okay, and then the pieces that we're missing would be this piece right here and this piece right here. Now my graph is not very nice, but on Desmos you can see that they add up to exactly what that middle is. Okay. All right, so the total area would be what? Total area would be double of that, right? So 4 root 2. Okay. All right, let me stop right here. Do you guys have any questions? Yes. Who's
You can do
raising
this
hand?
with any of the trig functions with each other, right? Because they all repeat. Or can you not do it with tangent?
So tangent, we could. It just depends. Do they bound something, right? As long as they
Right.
bound something, yes. So tangent is function. Let's see. Well, can we integrate tangent, right? Can we? Tangent is sine over cosine, yes. So we could do some u substitution, yes. The problem is that you should expect some functions that could be easily integrated. Okay, so notice that I'm not putting here sine square yet. We don't know how to integrate that yet, or cosine square. So you could do this, yes, for many functions. Okay. All right. Any other questions before we move on and solve a bunch other problems? How do you guys feel about trig in general? Integral of sine of 2x.
Slightly out of practice.
Yes. I mean, okay, you had a whole summer to forget a lot of things, so that's okay. So trig will be a big issue, not issue, but part of the class. So I see Zachary saying integral of sine of square x. Is that what it is? Sine square x was on homework. Was it on MyMathLab? Okay. All right, so let me take a look and see if I have a problem that I wanted to work out with sine squared. If not, I'll just add it. So let me just add another page. This is a good question. How do we integrate sine squared? Sine squared of x dx. Okay. All right, how do we integrate this function without knowing, let's say, a reduction formula, right? So there are reduction formulas that we'll discuss at some point, or without just plugging it into something like Wolfram alpha. Okay, so the answer for this one, we need to use double angle identities. Double angle identities. Okay. And it is something that I usually discuss with students during the first week of class. So I'm glad this was brought up. Okay. What are the double angle identities? So the double angle identity would be, okay, let's see if you guys remember what sine of 2t is 2 sine of t times cosine of t. So that's not very helpful. But what about cosine of 2t? Cosine of 2t. Okay, there's a couple of formulas that we could use. Okay, first it's cosine square of t minus sine square of t. It's good for you to know this formula, but in this case, it's not going to be very helpful for integration. The useful formulas are cosine of 2t is equal to this. So first, it's 2 cosine squared of t minus 1, or another form is 1 minus 2 sine squared of t. Okay, now from here you would be able to solve for cosine square or sine square. So in our case, we want to know sine square, right? So from here, if you were to solve for sine squared of t, so what do we get? Okay, so sine squared of t equal to what? 1 minus cosine of 2t divided by 2, right? You can do all the algebraic steps. I'm just solving for this expression. Now, this expression we can integrate because we just rewrote a quadratic form of our trig function in a linear function, right? So this is what? This is 1/2 minus cosine of 2t over 2. Okay, 1/2 is easy to integrate. Cosine of 2t over 2 is a function you can do with u substitution. Let's see, Victoria, is this going to be recorded? It's already, so yes, I haven't stopped recording. I'm still recording. The whole thing has been recorded. What's going to happen, about a couple hours later, it takes a bit of time to download the file and upload it on Blackboard, on YouTube first, then Blackboard. So yes, every session is recorded. Okay. So including the notes. The notes are going to be converted into PDF, then I'll load the PDF in week 1. So you'll see in week 1, everything is going to be there. All the lecture notes, the video links, and so forth. Okay, so sine square of t is this. So then now what you can do is say, okay, so the integral of sine squared of t dt is equal to the integral of 1/2 minus cosine of 2t over t dt. And that's easy to integrate, right? Okay, now you got rid of that power. Same thing for cosine squared. Cosine squared of t. If I solve it from one of these formulas that I just listed, okay, what's going to happen? That's going to be 1 plus cosine of 2t over 2. Okay, and you notice how these formulas are basically the same thing. It's for sine we have negative, for cosine we have positive. Okay, so that's how you approach a problem where you have sine squared. Okay, in chapter, which chapter is it? I think chapter 8, we're going to learn how to deal with all sorts of trig, all sorts of combination of powers and different expressions. But whenever you see just a square, this is it. You would use a double angle. Okay. All right. Good question. definitely ask questions like that. It's great. Okay, let's take a look at the next one. Okay, find the area of the region bounded by these trig functions. Okay, so I have secant squared x over 4 and 4 cosine squared. Okay, so here, there it is, where we're going to use one of these formulas. So again, I'm just to save a little bit of time so we can have as many examples as possible, I'm going to give you a sketch. Okay, so a sketch of this would look something like that. Okay, we're finding this area right here. Okay, this area is completely symmetric over the y-axis, which means you could make your computations a little bit simpler by saying, I'm just going to double one of the areas from 0 to whatever these points are. Okay, now these points, again, just use Desmos to find these points. You'll see that these points are from negative pi over 3 to pi over 3. Okay, so now we need to set up the area. You can also solve this algebraically. You can find these values algebraically. The area is, I'm going to double my integral from 0 to pi over 3. Okay, this is symmetric. They're the same. Okay, let's see. What do you guys think the top function is? If you had to guess, just based on the shape.
It's cosine or 4
Yeah.
cosine squared.
Yes, so good. So it's a good idea for you to kind of have that feeling, okay, I know what that function looks like, yeah? So cosine, notice it doesn't cross the x-axis, okay? It's positive, so that's a completely positive function. And then secant, remember the original function that's secant, it has these branches that go up and down. Now here, we're taking secant to the second power, so only positive branches. Okay, good. So that is your top function is the cosine squared minus secant squared over 4. That's the setup. And typically with these type of problems, that is the harder part, okay? Set it up correctly. So again, please use Desmos on quizzes, on homework, on exams as well. That's completely fine, okay? I'm not testing your graphical skills. I just want to make sure that you set it up correctly. So having a nice picture is definitely helpful. Set this up, find your limits of integration. Now we need to integrate. Okay, so there it is, 4 cosine squared of x. We just discussed it, right? So the area will be 2 times the integral of what? Okay, we can go back and say, what was that formula? 1 plus double angle of the cosine divided by 2, right? So it's 4 times 1 plus cosine 2, and what's our variable? X over 2 minus secant squared x over 4 dx. Okay. All right. Let's distribute that 4. That will get rid of some constants. So 2 integral from 0 to pi over 3. Once we multiply that 4, we cancel out, and we're going to get 2 plus 2 cosine 2x minus secant squared x dx. Okay, let me just check that I'm doing everything right. Looking good. Okay. All right, let's see. Now we'll integrate, right? Antiderivative of 2, that's 2x. Antiderivative of 2 cosine 2x. So the antiderivative of Cosine is sine, right? And the chain rule, so we apply the chain rule backwards here. Okay, so we're going to get sine of 2x. Okay. What about secant squared? Ooh, did I lose my constant? I did. Here we go. What is the antiderivative of secant squared? So here I'm asking. Anyone remembers? Secant squared. Tangent it is. Very nice. Minus quarter tangent x. This is one of the standard formulas that we should know, right? Derivative of tangent is secant squared. So the antiderivative of secant squared is tangent. Okay, good. We evaluate this from 0 to pi over 3. Okay, so you would plug in pi over 3 for x minus everything evaluated at 0. Now let's see, sine of 0 is thankfully 0. Tangent of 0 is also 0. So at 0, everything vanishes, right? Okay, I'm going to let you work out the algebraic steps, but you should get 4 pi over 3 plus square root of 3 over 2. That should be the final answer. Not a pretty answer, but okay. All right. So in this problem, I would definitely use a graphing utility. I do not expect you to be able to come up with these pictures by hand. Not at all. Okay. So use a graphing utility of your choice. Come up with a good picture. Say, oh, wait a minute, this is symmetric. Now, do you have to do it this way? No, you could have integrated it from negative pi over 3 to pi over 3, which is fine, but notice it's easy to evaluate things at 0. And that's one of the main reasons why we want to remember the symmetry, okay? It's easy to plug in 0 to anything, especially when everything just cancels out, okay? All right, what do you guys think? Any questions here? Nothing? Okay, then I'm going to skip this example only because I want to do a couple of examples where we integrate in a slightly different direction. So if you wish, try this on your own. And I can check your answer, or we can discuss it next time. But now let's take a look at this similar problem where now we have a function of y. Okay, so really fundamentally, we're not doing anything extremely different. What we're doing, we think about is rotating the plane, and now y is the independent variable and x is the dependent variable. That's all there is to it. Okay, as far as the actual mathematics and computations, we're not going to be doing anything too different. Okay, so let's go ahead and jump into example 5. We have the area of the region bounded by these two functions. Okay, so now we have x is equal to 2y squared. Okay, x is dependent, y is independent. So x is equal to 2y squared will look like a parabola that opens to the right. Okay, that's going to be one function, and then y is equal to 2 minus x over 2. Okay, let's see. Y is equal to 2 minus x over 2. I'm going to rewrite it as a function of y, so multiply everything by 2. That can be 2y is equal to 4 minus x. So x is equal to what? 4 minus 2y. Okay, and this function will look something like this. So we want to find the area of this piece right here. Okay, where now, how do we think about functions top and bottom? This is your positive direction. Okay, This is going to be your positive direction. This is your top. You can think about it as top. This is the negative direction, negative over here. Okay, that's the bottom. So your top function will be the linear function. This is the top function. And this one is the bottom function. Okay. All right. So again, fundamentally, nothing is different from what we've done before, except that think about the rotation of the plane. Really, that's all that happened. We relabeled our axes. Now x is dependent, y is independent, and it might be a little bit more challenging to determine which one is top, which one is bottom. Okay. All right. So what is the area here? Area is the integral. The top function is 4 minus 2y. The bottom function is the parabola minus 2y squared dy. And we need to find the limit, right? So that would be these points right here. Okay. And the nice thing about Desmos, again, it will produce any function, whether it's a function of x or a function of y. It will do what you want it to do. So calculators only do function of x, right? But in this case, in Desmos, just type it in just like that, and then it will produce the picture that looks just like my sketch over here. So once you find your points, this one will be 1, and this one will be negative 2. Okay, now notice that now we'll look at the range on y-axis. That's our variable that changes, right? That's our independent variable. Okay, so our limits of integration are from -2 to 1. Okay, that's the setup. The rest is easy. This is a polynomial function. It's easy to integrate. So it's 4y minus y squared minus what, 2 over 3 y cubed. We evaluate this between -2 and 1. Again, I'm going to let you can use your calculator to plug this in. I'm going to get 9 units. Okay. All right. So this is your example where you have different orientation of the plane. You can think about it this way. Okay. What do you guys think? Any questions here? Anything not clear? What's the general consensus? Is this okay? Not hard yet? Not easy? So far, so good. Okay, thank you. I appreciate any feedback you guys give me. All right, let's do one more question. Let's see what else I got. 7, 8. No, I got tons of problems, but no, let's see. Let's do this one, the one with the absolute value. Okay, and if we have some problems that are left over, you guys can work on it on your own if you wish. And then we can check the answers. So let's see what we got here. We have x is equal to absolute value of y, and then the other function is 2 minus y squared. Okay. Absolute value of y. So here's your v function, right? This is x, this is y, and 2 minus y squared. This is a parabola that opens down, but it starts at 2 over here, and then it opens down this way. Okay, that's your new down, right? Okay, negative direction, this is positive direction. Okay, once again, this area right here is symmetric, but now it's symmetric across the x-axis. Okay. Once we find our points where they cross, this would be 1, this would be -1, completely symmetric. You could set it up as a single integral from 1 to -1, or from -1 to 1, or you could double it. Either way, you should get the same thing. Okay, so area is equal to 2. I'm going to go from 0 to 1. 2 minus y squared. That's going to be my top, right? This is the top. And then this, the linear function, is the bottom. Okay. Now, actually, in this case, we should split it up. And why is that? Remember that the absolute value function is really a piecewise defined function. Okay. So it's equal to y on the positive side, but it's equal to negative y on the other side. Okay, so what do you plug in here? Can we plug in absolute value of y? We can't do that, right? We have to plug in either y or negative y, depending on which side we're on. Okay, from 0 to 1, since y is positive on this side, that means we just plug in y. Okay, y dy. And now the rest is easy. We just need to integrate a polynomial function. So this is 2y minus 1/3 y cubed minus 1/2 y squared. Okay, and we go from 0 to 1. At 0, everything vanishes, so this is 2 minus 1/3 minus 1/2, and then we double this. Once you guys do the arithmetics, you should get 7/3 units, and you can check with your calculator. Okay, all right. So here's another problem where we have a slightly different orientation. Okay, any questions here? Anything you guys want to discuss? All good? All right, well, let's see what we have here. I have 2 problems. Okay. What should we do? Do you guys want to try on your own? You want to try these? Somebody give me any indicator if you want to do it or no.
Might as well.
Okay, so how about, let's see, well, there's 10 of you. Just pick one, okay? Pick whichever one you want. And you will need to use Desmos to graph these because, you know, they're quadratic and they're not really simple. So I would use Desmos and see if you can give us an answer, okay? So why don't you guys pick one, work it out, and then if you come up with an answer, definitely let me know what you get, and then we'll compare the answers. Okay? All right, let's see. Why don't we just all pick example 7? So we're all working on the same part. And then example 8 is a little bit more involved. So let's do 7. I wonder if I can pause the recording for a second. It's hard to tell. Okay, so I at least got a picture for you guys. Here's the image. Okay. Hello, can you guys hear me? Yes, great. Okay, thank you. I muted myself for a little bit because my dog was going wild. Okay, so here's the image. Does anyone have the limits of integration yet?
Is it -3 to 2?
Good. So -3 to 2, those are the limits. Okay, so let me go ahead and write it. Okay, so here's the brief sketch. Okay, so something like this. Here's the area. We go from -3 to 2. Okay, so area would be the integral from -3 to 2. Okay, and what do you guys get for your integrand? What's the top function?
The top function is -2y squared minus 6y plus 30.
Okay. Then the bottom is the other one, right? So,
Indeed.
okay. Plus, oh, this would be minus, right? So minus 3y minus y squared plus 3y minus 12 dy. Okay. So we got to simplify this first, right? So the integral from -3 to 2, combine like terms, we get -3y squared. What else? Minus 3y and plus 18. Is that right? Okay. Does anyone have an answer yet? If you don't have an answer, that's okay.
Nope.
No answer yet? Okay. Zachary, go ahead. What did you get? 57. Okay, I did not get 57, so let's see if our antiderivative is the same. So the antiderivative should be what? -y cubed, right? Minus 2/3 y squared plus 18y. Okay, that's the antiderivative. We got to evaluate this from -3 to +2. Okay, from -3 to +2. So for this one, just use your calculator. Okay, I got 125 divided by 2. So what is that? 62.5, right? I got 125 over 2. Did anybody else get this? Now let's see. Zachary, is your antiderivative the same? Did I lose connection? Am I still here?
I can still.
You're still good.
Okay, good. Okay, so your antiderivative is the same. Yeah, so again, if this is just like the last step of your evaluation, no biggie, okay? Just double check with your calculator real quick. Okay, so do we have anybody who came up with that answer? 125/2. That should be the answer. Okay, well, I'm gonna let you check, guys. But if you have your antiderivative and the evaluation from -3 to 2, that's 99% of the work. That's done. Okay, so that's good. All right. Okay, it's 2:40. I'm gonna go ahead and stop the official recording, but then I'm gonna hang out for about a couple more minutes to see if there are any other questions. So let me go ahead and stop this.